Hello, in this lecture I will answer two questions. The first question, we find out the area of this green shape that is inside square TSQP. And the second question, we find out the area of this green shape that is inside square ABCD. So let's start with the first question. In the drawing we have two squares. TSQP is a square and ABCP is also a square. We know that the area of this right triangle MAP is equal to 9 square units in size, and the area of this quadrilateral MBCP is equal to 27 square units in its size. And our task is to find out the area of this green shape. So, first of all, we know that the area of this small square ABCP is equal to the area of the right triangle AMP, that is 9, plus the area of this quadrilateral MBCP, that is 27. So in total, the area of this small square ABCP will be equal to 9 plus 27, that is 36 square units in its size. So we write it down. The area of the small square ABCP is equal to 9 plus 27, that is 36 square units in its size. And we also know that the area of any square equals to the length of one side squared. So the area of this square ABCP will be equal to the length of AP squared. So the area of square ABCP is equal to the length of side AP squared. But we know that the area equals to 36 square units in size, so we can write here that the area equals to also 36 square units in size. And for this equation, we have that AP equals to AP squared equals to 36. Here we take a root out of this equation, and we get that AP, the length of side AP of square ABCP, is equal to the square root of 36, that is 6. Simply, this is side AP, is equal to 6 units in its length. Write it down. AP equals to 6. So, in the next step, we focus on the right triangle, triangle AMP. This is the right triangle, triangle AMP. It is given us the question that the area of this right triangle AMP is equal to 9 square units in its size. So, we calculate the area of this right triangle according to the area of a triangle is equal to the base of the triangle, that is AM, times the height of the base, that is AP, over 2. So the area of the right triangle AMP is equal to the base, that is AP, times the height, that is AM, over 2. Read again. The area of the right triangle AMP equals to the base AP times the height AM over 2. But it is given as a equation that the area equals to 9 square meters inside. So can I say that the area equals to 9, AP equals to 6, so we substitute AP by 6, so 6 times AM, the height AM over 2 equals to 9, that is the area of the right triangle AMP. 6 over 2 is 3, so this expression equals to 3 times AM equals to 9. Here we divide this expression by 3 and we get that AM equals to 9 over 3 is 3. So this is side AM is equals to 3 units in its length. So now we'll implement the Pythagoras theorem in order to find out the length of the hypotenuse MP of the right triangle AMP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, I'll copy the right triangle AMP in a new equation. We will implement on this right triangle AMP the Pythagoras theorem. I want to explain that this is angle BAP is equal to 90 degrees in its size because of the fact that all the angles inside the square are right angles. So it is 1 out of 4 angles of square ABCP and therefore it is equal to 90 degrees in its size. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle AMP, the point from the original drawing. We already found out that AM equals to 3 and AP equals to 6. The hypotenuse MP is the only missing side. So according to the Pythagoras theorem, in this right triangle AMP, MP square equals to AM square plus AP square. So right now, MP square, that is the square of the hypotenuse, equals to AM square plus AP square. MP is the missing side, so it is MP square equals to AM square. AM is 3, therefore AM square is 3 squared, that is 9, plus AP square. AP is 6, therefore AP square is 6 squared, that is 36. 9 plus 36 is 45. So if you remember that MP square equals to 45. Here we substitute 45 by 9 times 5 and get that MP square equals to 9 times 5 here we'll take a root out of this equation. And finally we get that the missing hypotenuse MP is equal to the square root of 9 times 5. The square root of 9 is 3, so inside the root we'll have to only be 5. So in total we should find out that the length of the hypotenuse MP is equal to 3 times square root of 5 units in its length. MP equals to 3 times square root of 5 units in its length. We know that all the angles inside the square are right angles, so in the big square TSQP, this angle equals to 90 degrees in its size. So we'll focus on the next step on those two right angles, TBM, and the right angle APM. Those two angles, they'll define the vertex angles. When we know that vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that vertex angles are equal to each other. So in the right angle, the right small triangle TMP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in a triangle is equal to 180 degrees. That is to say, 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the right triangle AMP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha, according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see from the drawing that those two right angles are similar to each other according to angle similarity rule. That is to say, the small right triangle TMB is similar to the big right triangle AMP. So I will explain anyway why those two right triangles are similar to each other. First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So if you found out that all the angles of the small right triangle TMB are corresponding equal to all the angles of the right triangle, the right big triangle AMP, therefore those two right triangles are similar to each other according to angle similarity rule. So okay, now if you found out that the big right triangle AMP is similar, this is the sign of similar to the right triangle, the small right triangle TMB, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle AMP over side MB of the small right triangle TMB equals to side MP of the big right triangle AMP actually we derive that side AP of the big right triangle AMP over side TB, or side TB of the small right triangle TMB equals to side MP of the big right triangle AMP over side MB of the small right triangle TMB, and it is also equal to side AM of the big right triangle AMP over side TM of the small right triangle TMB. Again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive the side AP of the big right triangle AMP over side TB of the small right triangle TMB equals to side MP of the big right triangle AMP over side MB of the small right triangle TMB, and it is also equal to side AM of the big right triangle AMP over side TM of the small right triangle TMB. Before we continue, we find out the length of side MB. MB equals to AB minus AM. So I don't know, side MB, this is the missing side MB, this is equals to AB minus AM. So MB in total equals to AB. We know that all the sides of square ABCP are equal to each other. Side AB equals to 6, and therefore side AB must be also equal to 6. So MB equals to AB, that is 6, minus AM, that is 3. So in total MB equals to 6 minus 3, that is 3. MB equals to 3 units in its length. The missing side MB equals to 3 units in its length. So from the fact that those two right triangles are similar to each other, we derive that side AP of the big right triangle AMP over side TB of the small right triangle TMB equals to side MP of the big right triangle AMP over side MB of the small right triangle TMB, and it is also equal to side AM of the big right triangle AMP over side TM of the small right triangle TMB. AP is 6, over TB. TB is the missing side, so leave it as it is, and it is equal to MP. MP equals to 3 times square root of 5 units in its length over MB. We just write down further that MB equals to 3, and it is equal to AM, that is 3, over TM. TM is the missing side, so leave it as it is. So if we found out that 6 over TB equals to 3 over square root of 5 equals to 3 times square root of 5 over 3, and it is equal to 3 over TM. We have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. And after we cancel 3, we actually found out that 6 over TB equals to the square root of 5. Those two sides are equal to each other. That is to say 6 over TB equals to the square root of 5. Here we will multiply this equation by TB, and then we divide it by square root of 5 simultaneously, and we get that TB equals to 6 over square root of 5 units in its length. TB equals to 6 over 4 to 5 units in its length. Those two sides also equal to each other. So we get the second equation from those two sides that are equal to each other. That is to say, square root of 5 equals to 3 over Tm. Here we multiply this equation by Tm, and then we divide it by square root of 5, and we get that Tm equals to 3 over square root of 5 units in its length. So this is the missing side Tm. This equals to 3 over square root of 5 units in its length. And this is the missing side Tb. This equals to 6 over square root of 5 units in its length. So what is the length of side TP? TP equals to Tm plus MP. Again, TP equals to Tm plus MP. So that's the norm. The length of one side of the big square TSQP will be equal to TP, and TP equals to Tm plus MP. TP equals to Tm plus MP. So the length of one side of the big square TSQP, that is TP, this equals to Tm plus MP. So TP in total equals to Tm. Tm is 3 over square root of 5 plus MP. MP equals to 3 times square root of 5. So in total, we found out that one side, the length of one side of the big square TSQP, that is TP, is equal to 3 times square root of 5. 3 times square root of 5 plus 3 over square root of 5. So TP equals to 3 over square root of 5. Here we will multiply this expression by square root of 5, and then we divide it by square root of 5, and we get that we have in the denominator square root of 5, and in the numerator we have square root of 5 times square root of 5, that is 5, and 5 times 3 is 18. 5 times 3 is 15. So in the numerator we have 5 plus 15, that is 18 over square root of 5. So in total, if you want to know that TP equals to 18 over square root of 5 units in its length. So one side of the big square TSQP is equal to 18 over square root of 5. And our task is to find out the area of this green shape. So what is the area of the green shape? It is very easy to see from the drawing that the area of this green shape equals to the area of the big square TSQP minus the area of this quadrilateral MBCP, that is equals to 27 square inches in size. Minus the area of this small right triangle TMB. Repeat again. The area of the green shape, that is the area that we are looking for in this question, in total will be equal to the area of the big square TSQP minus the area of quadrilateral MBSP. It is given us a question that the area of quadrilateral MBCP is equal to 27 square inches in size. minus the area of the right triangle TMB, the small right triangle TMB. So the area of the green shape in total equals to the area of square TP SQ. We know that the area of any square equals to the length of one side square, so it will be equal to TP squared minus the area of this quadrangle MBCP, this is 27 square units in its size, so it is minus 27, minus the area of this small right triangle TBP, the area of this right triangle TBM, the small right triangle TBM equals to the base TB times the height TM over 2. So in total, if you want to know that the area of the green shape equals to the area of square TSQP, that is also TP squared, one side squared, minus the area of quadrangle MBCP, that is 27 according to all this equation, minus the area of the small right triangle TMB, this is equals to the base of the triangle that is TB times the height to the base TM over 2. We already found out that TP equals to 18 over square root of 5. So TP squared will be equal to 18 over square root of 5 squared minus 27 minus the area of the small right triangle TMB is equals to TB. TB is 6 over square root of 5 times TM, that is 3 over square root of 5. And again, TB equals to 6 over square root of 5 times TM, that is 3 over square root of 5 divided by 2. So in total, we should know that the area of this green shape equals to the area of the big square TSQP, that also equals to 18 squared over square root of 5. 18 squared is 324 over square root of 5 squared is 5 minus 27, and we have here minus 6 times 3 is minus 18, and we have the amount of square root of 5 times square root of 5 is 5, and 5 times 2 is 10. 324 over 5 equals to 64.8 square units in its size, minus 27 minus 18 over 10 is minus 1.8. And we have 64.8 minus 1.8 is 63. 63 minus 27 is 36. Yep, 63 minus 27 is 36. So in total, we should find out that the area of the green shape equals to (36) square units in its size. And again, I should find out that the area that we are looking for in this question, that is the area of this green shape, equals to 36 square units in its size. So we finished with the first question. In the next step, I will present you the second question and solve the second question of this lecture. In the second lecture, in the second question, our task is to find out they have this shape that is inside square ABCD. So in the drawing we have the big square ABCD. Inside, we know that one side of square ABCD equals to 10 units in its length. Inside this square ABCD we have this quarter circle, and we also have this semicircle. And our task is to find out they are of this green shape. So first of all, BC is one side of square ABCD, and it is equal to 10 units in its length. BC is also the diameter of this semicircle. This is equal to 10. If the diameter is 10, then the radius must be equal to 10 over 2, that is 5. So the radius of this semicircle equals to 5 units in its length. We will find the center of this semicircle, this point as O. So the radius OB equals to 5 units in its length. The radius OC also equals to 5 units in its length. We know that point A is the center of the quarter circle. Again, point A is the center of the quarter circle. Point B is the point of the quarter circle itself. Therefore, AB is the radius of the quarter circle. This is equal to 10 units in its length. AD is also the radius of the quarter circle. It's equals to 10. Likewise, DC also equals to 10 because ABCD is a square. So, in the next step, we will define the intersection point between the quarter circle and the semicircle. This point is point M. And we'll join points A and M together by a straight line. What is the definition of line segment AM? AM is tangent to this semicircle at point M. Again, AM is a tangent to this semicircle at point M. In the next step, we join points O and M together by a straight line. Point O is the center of the semicircle, point M is the point of the semicircle itself, therefore OM is the radius of this semicircle. This equals to 5 units in its length. Here we can implement rule 1 because of the fact that the radius OM of the semicircle is equals to 5. The radius OM is drawn to point M, that is the point of tendency of tangent AM with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AM will be perpendicular to the radius MO. If AM is perpendicular to MO, it means that this angle equals to 90 degrees in its size, according to rule 1. Again, because of the fact that the radius OM is drawn to point M, that is the point of tendency of tangent AM in this semicircle, and whenever your radius is drawn to the point of tendency, then tangent AM will be perpendicular to the radius MO. If AM is perpendicular to MO, it means that this angle equals to 90 degrees in its size, according to rule 1, of course. Our task is to find out they are of this green shape. So first of all, we join points M and B together by straight line. By joining points M and B, we divided the green shape into two segments. This is the upper segment and this is the lower segment. So we define the upper segment as segment BUM. U is a version for upper, and we define the lower segment. This is the lower segment, a segment BLM. And is a version for lower. So by doing this construction, we have there two segments, the upper segment BUM and the lower segment BLM. We will find out the area of each segment separately and then we'll add the two areas together, and this will give us the area of the green shape, of course. So we'll start with the small segment BLM. What is the area of the small segment BLM? So first of all, I'll copy sector A and B, and then we'll analyze this sector A and B. Actually, in square ABCD, this angle is a right angle. But before I copy segment sector ABM in a new page, we'll join points A and O together by straight line. By joining points A and O together, there two right angles. This is the big right angle AOB, and this is another big right angle AOM. We know that point A is the center of the quarter circle, point M is the point of the quarter circle itself, therefore AM is the radius of the quarter circle, is equal to 10 units. So, in the next step, we'll prove that those two right angles can go into each other according to side rule. Okay, again, we'll prove that the right angle ABO can go into the right angle AOM according to side rule. So we prove that the right angle ABO, this is the right angle ABO, this is congruent to this right angle AOM according to side rule. So why those two right angles can go into each other? First of all, side OB of the right angle ABO equals to side OM of the right angle AOM. They are both equal to 5 and therefore they are equal to each other. Are actually the radii of the semicircle. So OB equals to OM equals to 5. In addition, side AB of the right angle AOB equals to side AM of the right angle AOM, they're both equal to 10 and therefore they're equal to each other. So AB equals to AM equals to 10. And again, side AB of the right angle ABO equals to side AM of the right angle AOM, they're both equal to 10 and therefore they're equal to each other. And finally, side AO is a common side that belongs to both triangles. So can I know that AO equals to itself is a common side that belongs to both triangles? If the again side AO equals to itself, it's a common side that belongs to both triangles. So if you prove that all the three sides of the right triangle ABO are correspondingly equal to all the three sides of this right triangle AOM and the right triangle AOM, and therefore those two right triangles can go into each other according to side rules. So, okay, now if you know that the right triangle ABO congruent, this is the sign of congruent to the right triangle AOM according to side rule. And from the fact that those two right triangles can go into each other, we will derive that those two angles are equal to each other. Those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. Corresponding angles in congruent triangles are equal to each other. Likewise, because of the fact that those two right triangles can go into each other, we will have that those two angles must be also equal to each other according to the same rule that corresponding angles in congruent triangles are equal to each other. So if you define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to the rule that I mentioned. In the next step, we'll focus on the right triangle AOB. In the right triangle AOB, the sum of the angles must be equal to 180 degrees. So which angles we have in the right triangle AOB? We have alpha plus beta plus 90 degrees. In total must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Again, in the big right triangle AOB, this right triangle AOB, the sum of the angles must be equal to 180 degrees, so alpha plus beta plus 90 degrees must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and we get that alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. So alpha plus beta equals to 90 degrees. Here we subtract alpha from this equation, and we get that angle beta equals to 90 degrees minus alpha. So in the next step, we find out the values of angle alpha and angle beta. In order to find out the sizes of angles alpha and beta, we focus on this big right triangle AOB. In the big right triangle AOB, sinus alpha, the big right triangle AOB, sinus alpha equals to BO over OA. Repeat again. In the big right triangle AOB, sinus alpha equals to BO over OA, that is the hypotenuse. But first of all, we'll implement the Pythagoras theorem on this big right triangle ABO in order to find out the value of the hypotenuse AO. And again, we'll implement the Pythagoras theorem on this big right triangle AOB in order to find out the value of the hypotenuse AO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So AO squared, that is the square of the hypotenuse equals to AB square plus BO square. And again, in the right triangle AOB, only to the Pythagoras theorem, AO square, that is the square of the hypotenuse, equals to AB square plus BO square. AO is the missing side, so leave it as it is, so it is AO square equals to AB square. AB is 10, therefore AB square is 10 squared, that is 100, plus BO square. BO is 5, therefore BO square is 5 squared, that is 25. So in total, we should know that AO square equals to 100 plus 25, that is 125. So AO square equals to 125. Here we substitute 125 by 25 times 5. So we found out that AO square equals to 25 times 5. Here we take a root out of this equation. And finally we get that AO equals to the square root of 25 is 5. So inside the root we left only 5. So it is 5 times square root of 5. So if you find out that the length of the hypotenuse AO is equal to 5 times square root of 5 units in its length. This is the hypotenuse AO is equals to 5 times square root of 5 units in its length. We return to the right triangle ABO. So in the right triangle ABO, we know that sinus alpha equals to BO over AO. And again, in the right triangle AOB, sinus alpha equals to BO over AO. So what is here? In the right triangle AOB, sinus alpha equals to BO over AO. In the right triangle ABO, sinus alpha equals to BO over AO. So sinus alpha equals to BO. BO is 5 over AO. We just write down further that AO equals to 5 times square root of 5. So in total, we should find out that sinus alpha equals to 5 over 5 times square root of 5. We have 5 in the numerator, 5 in the denominator, so 5 will get cancelled, and we left only with 1 over square root of 5. So in total, we should find out that in right triangle AOB, sinus alpha equals to 1 over square root of 5 units in its length. Read again. I should find out that sinus alpha equals to 1 over square root of 5 units in its length. Sinus alpha equals to 1 over square root of 5. Our test is to find out the value of angle alpha itself, the size of angle alpha. In order to find out the size of angle alpha, we will operate the opposite function of sine, that is arc sine, on the result that is 1 over square root of 5. In this way, we get the value of alpha. So the opposite function of sine is arc sine. Arc sine will operate the opposite function of sine, that is arc sine of the result that is 1 over square root of 5. This will give us the value of alpha. And arc sine of 1 over square root of 5, you can find it in any calculator. It is equals to alpha equals to 26 56.565 degrees. Again, arc sine of arc sine of 1 over square root of 5 is alpha, and arc sine of 1 over square root of 5 equals to 26.565 degrees. So if you want to know that alpha, this is angle alpha, is equal to 26.565 degrees. So if alpha equals to 26.565 degrees, it means that 2 alpha will be equal to 2 times 26.565. That's actually 53.13 degrees. So if you found out that the big angle, alpha plus alpha is 2 alpha, the big angle BOA, the big angle BAM is equal to 2 alpha, is equal to 53.13 degrees in its size. We have already found out that angle beta equals to 90 degrees minus alpha. So beta equals to 90 degrees minus alpha. So beta equals to 90 degrees minus alpha, and alpha equals to 26.565, and 90 degrees, 26.565 degrees, and 90 degrees minus 26.565 is equal to 63.435 degrees. So if you know that angle beta equals to 63.435 degrees in its size, if beta equals to 63.345 degrees, it means that 2 beta will be equal to 2 times 63.345, is actually equals to 126.87 degrees in its size. So actually, this is the big angle MOA or BOA, that equals to 2 beta, and 2 beta equals to 126.87 degrees in its size. Again, angle MOB equals to 2 beta, and 2 beta equals to 126.87 degrees in its size. Our task is to find out the area of this green shape. So, in the next step, we'll find out the area of segment, the lower segment MLB. We'll find out the lower segment MLB. So, I'll copy sector A and B in a new page, and we'll find out the area of the lower segment MLB. This is the lower segment. This is angle 2 alpha. The big angle is 2 alpha. This is equals to 53.13 degrees in its size. So actually, this is sector A and B. There's a comment from the original drawing. And again, this is sector A and B. There's a comment from the original drawing. And our task is to find out the area of this segment, segment BLM. Again, our task is to find out the area of this green segment BLM. Segment BLM. So we have to find out the area of this green segment BLM. And this is sector A and B. So first of all, what is a sector? A sector is a portion of a circle with two radii that enclosed with two radii and the arc between them. Again, a sector is a portion of a circle enclosed by two radii and the arc between the two radii. AM equals to 10, the radius of the quarter circle. AB also equals to 10. This is also the radius of the quarter circle. You can see here that sector A and B has two legs, the two radii of the quarter circle, each of them equals to 10. And the arc between the two radii is this arc. You can see that the green sector AOB is a portion of a circle. It consists of two radii. Those are the two radii of the circle. And the arc between the two radii, that is arc AB. And the angle between the two radii, that are the two legs of the sector, is angle theta. So, what is the area of sector AOB? The area of sector AOB equals to the area of the circle that contains the sector, that is actually pi r squared, because r is the radius, times the angle between the legs of the sector, that is theta, over 360 degrees. Repeat again. The area of this green shape AOB, that is actually the area of sector AOB, equals to the area of the circle that contains the sector, that is actually pi r squared, times the angle between the legs of the circle, that is theta, over 360 degrees. So, in conclusion, we found out that a sector is a portion of a circle enclosed by two radii, and the arc between the two radii, that is arc AB. And the area of the two radii are defined as the legs of the sector, and the area of sector AOB will be equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the two legs of the sector, that is theta, over 360 degrees. So we use the new formula in order to find out the area of this sector, sector A and B. So what is the area of sector A and B? The two legs of sector ABM are the eye of the quarter circle, each of them equals to 10, because the radius of the quarter circle equals to 10. So the area of the sector ABM will be equal to pi r squared, that is the area of the circle that contains the sector. R is 10, of course, is the radius of the quarter circle, times the angle between the two legs of the circle, that is 53.13 degrees over 360 degrees. Repeat again. The area of the sector ABM in total equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 53.13 degrees over 360 degrees. Again, r is 10, it is the radius of the quarter circle, that is 10, therefore r squared is 10 squared, that is 100, and therefore pi r squared is 100 pi times 53.13 over 360 degrees. So in total, we should find out that the area of this sector ABM is equal to 100 pi times 53.13 degrees over 360 degrees. Actually, the value of this expression in total is equal to 36. It is equal to 46.3646 square units in size. Repeat again. The area of this sector ABM in total it is equal to 46.3646 square units in size. Our task is to find out the area of the green segment BLM. So what is the area of segment BLM? This is the green segment BLM. What is the area of this segment BLM? From the drawing, it is very easy to see that the area of the green segment BLM, that is the lower segment. This is the lower segment BLM. The area of this segment BLM equals to the area of the big sector ABM. This is the big sector ABM. Minus the area of triangle ABM. The area of this triangle ABM. Again, it is very easy to see from the drawing that the area of this segment BLM, the lower segment, equals to the area of the big sector ABM minus the area of triangle ABM. It is very easy to see that if you subtract the area of triangle ABM from the area of the sector ABM, we get exactly the area of segment BLM. We already found out that the area of this big segment AMB is equal to 46.3646 square units in size. So you know the area of this sector ABM equals to 46.3646 square units in size minus the area of triangle ABM. This is triangle ABM, that's going to be in the triangle here. So, in the next step, I will present to you a new formula in order to find out the area of any triangle. This is triangle ABC, that could be any triangle. In triangle ABC, side AB equals to A units in its length, side AC equals to B units in its length. This is angle BAC, that equals to theta degrees in its size. The area of this triangle ABC that could be any triangle equals to A times B, that is the multiplication of the two sides by each other, times the angle between the two sides, that is theta, or times sinus theta over 2. And again, the area of this triangle, triangle ABC, that could be any triangle, equals to the multiplication of the two sides by each other, that is to say A times B, times sinus the angle between the two sides, that is sinus theta over 2. So if we found out that this triangle ABC, that could be any triangle, equals to A times B, times sinus the angle between the two sides, that is sinus theta over 2. We use the new formula in order to find out the area of this triangle, triangle ABM. According to the formula that I presented to you, the area of this triangle ABM will be equal to the multiplication of the two sides by each other, that is to say it is AB times AM times sinus the angle between the two sides, that is sinus 53.13 degrees divided by 2. This equation is the implementation of the new formula in order to find out the area of this triangle ABM. So it is AB times AM times sinus angle 53.13 over 2. AB is 10, AM is also 10 over 2 times sinus 53.13 degrees. Sinus 53.13 degrees is equal to 0.8. So total, the area of this triangle ABM, that is actually an isosceles triangle, equals to 10 times 10 over 2 times 0.8. 10 times 10 is 100, 100 over 2 is 50, and 50 times 0.8 is 40. So if you found out that the area of this triangle ABM equals to 30 square units in its size, and the area of segment BLM, the area of the lower segment BLM equals to the area of sector ABM minus the area of triangle ABM. The area of sector ABM equals to 46.3646 minus the area of triangle ABM equals to 40 square units in its size. So 46.3646 minus 40 is equal to 6.3646 units in its size. So in total, we should know that the area of this segment BLM equals to 6.3646 square units in its size. And again, we should find out that the area of this lower segment BLM equals to 6.3646 square units in its size. So in the next step, we'll find out the area of the upper segment BUM. The area of this upper segment BUM. In order to find out the area of the upper segment BUM, I'll copy sector BOM in a new page. We already found out that 2 beta equals to 126.87 degrees in its size. So actually, this is sector BOM that according to the original drawing and the length of the sector OB equals to OM equals to 5. Here, OB equals to OM equals to 5. Above the radius of the semicircle, this equals to 5. So OB equals to 5. OM also equals to 5, and the angle between the two radii, that is to say the angle between the lengths of the sector, is 126.87 degrees in its size. According to the formula that I presented to you a couple minutes ago, the area of this sector BOM must be equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 126.87 degrees over 360 degrees. R is 5, therefore r squared is 5 squared, that is 25. So pi r squared is 25 pi times 126.87 degrees over 360 degrees. So the area of this sector BOM, here the rounded sign above BOM is the sign for a sector. So the area of this sector BOM, in total it is equal to 25 pi times 126.87 degrees over 360 degrees. Actually, in total, the value of this expression, in total, it is equal to 27.678 square units in its size. So if you found out that the area of this sector BOM equals to 27.678 square units in its size. That is the area of the upper sector B. That is the area of the upper sector BOM. This is the area of the upper sector BOM. Actually, it is sector BOM. Okay. So the area of sector BOM equals to 27.678 square units in its size. Our task is to find out the area of this green segment, the upper segment BOM. So what is the area of this green upper segment BOM? What is the area of this green upper segment BOM? From the drawing, it is very easy to see that the area of this green upper segment BOM equals to the area of the big sector BOM. This is sector BOM minus the area of triangle BOM. Repeat again. The area of the upper sector BOM equals to the area of sector, the area of the upper segment BOM, this segment BOM is equal to the area of sector BOM, this is sector BOM, minus the area of target BOM. We already found out that the area of sector BOM equals to 27.678 degrees in its size. the angle between the legs here 126.87 degrees. Here also and BO equals to OM equals to 5. So minus the area of the associated triangle BOM. According to the formula that I presented to you a couple of minutes ago, the area of this triangle BOM equals to BO times OM times sinus the angle between those two sides, that is actually 126.87 degrees over 2. BO is 5, OM is also 5, sinus 126.87 is 0.8 divided by 2. So in total, if you know that the area of this triangle BOM equals to 5 times 5 over 2 times 0.8. 5 times 5 is 25. 25 over 2 is 12.5. And 12.5 times 0.8 is equal to 10. So if you found out that in total the area of this triangle BOM equals to 10 square units in its size. And the area of segment BOM equals to the area of sector BOM, that is 27.678 square units, minus the area of this triangle BOM, that is 10 square units. 27.678 minus 10 is 17.67 square units in its size. So in total, we found out that the area of the upper segment BOM equals to 17.678 square units in its size. So this is the upper segment BOM, and the area of the upper segment BOM equals to 17.678 square units in its size. Now the test is to find out the area of this green shape. So the area of the green shape in total equals to the area of the upper segment BOM, that is 17.678, minus the area of the lower segment BLM, that is equals to 6.3646 square units. So until again, I should find out that in total the area of the green shape is equal to the area of the upper segment BOM minus, plus the area of the lower segment BLM. And again, the area of this green shape equals to the area of upper segment BOM plus the area of the lower segment BLM. The area of the upper segment BOM equals to 17.678 degrees square units in its size, plus the area of the lower segment BLM, that actually equals to 6.3646 square units in its size. So the area of this green shape in total equals to the area of the upper segment BOM, that is actually 17.678 square units in its size, plus the area of the lower segment BLM, that is equals to 6.3646 square units in its size, and 17.678 plus 6.3646. In total, it is equal to 24.0426 square units in its size. So the answer to the question is that the area of this green shape, that is the area that you are looking for in this question, It is equal to 24.042 square inches in size. Repeat again. The area of this green shape equals to 24.042 square inches in size. So we finish with the second question. In the next step, I'll start with the next one. We'll start with the first question, of course. In the first question, our task is to find out the area of this green shape. So in the drawing, we have two squares. We have the big square TSQP and the small square ABCP. In addition, you know that this is quadrangle MBCP is equals to 27 square inches in size, and this is the right triangle MAP is equals to 9 square inches in size. Again, our task is to find out the area of this green shape. So first of all, we know that the area of the small square ABCP equals to 9 plus 27, that is 36 square inches in size. And we know that the area of any square equals to the length of one side squared. Again, the area of any square equals to the length of one side squared. Therefore, the area of this square ABCP will be equal to AP, the length of side AP squared. So the small square ABCP equals to 9 plus 27, that is 36 square inches in size, and the area of square ABCP equals to the length of one side, that is AP squared. And know that the area of square ABCP equals to 36 square inches in size. For this equation, we know that AP squared equals to 36. Here we took a root out of this equation, and found out that the length of side AP is equal to the square root of 36, that is 6. And side AP equals to 6 units in its length. In the next step, we implemented, we found out the area of this right triangle A and B. The area of this triangle, the right triangle A and P. The area of the right triangle A and P equals to the base AP times the height AM over 2. Repeat again. The area of this right triangle A and P equals to the base AP times the height AM over 2. Repeat again. The area of the right triangle A and P equals to the base AP times the height AM over 2. But it is given in the question that the area of this right triangle A and B equals to 9 square inches in size. So can I write out that the area of the right triangle A and P equals to 9 square inches in size, according to what is given in the question, and the area equals to the base AP times the height AM over 2. AP is 6, AM is the resistance side, so we leave it as it is, divided by 2. So in total, we should know that 6 AM over 2 equals to 9. 6 over 2 is 3, so 3 AM equals to 9. Here we divided this equation by 3 and found out that AM equals to 3 units. Let me see side AM equals to 3 units in its length. In the next step, I copied the right triangle AMP and we implemented on this, in the new page, we implemented the Pythagoras theorem in this right triangle AMP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is the right triangle AMP that I copied from the original drawing. According to the Pythagoras theorem, this right triangle AMP, AP squared, that is the square of the hypotenuse, equals to AM squared plus MP squared. AP we have AP squared AP square equals to AM square plus MP square. Actually, it is MP. The hypotenuse is MP. MP square equals to AM square plus AP square. MP is the missing sign, so it is. So MP square equals to AM square. AM is 3, therefore AM square is 3 squared, that is 9, plus AP square. AP is 6, therefore AP square is 6 squared, that is 36. So in total MP square equals to 9 plus 36, that is 45. So MP square equals to 45. Here we substitute 45 by 9 times 5, and found out that MP square equals to 9 times 5. Here we took out of this equation, and finally found out that the missing hypotenuse AP equals to the square root of 9, that is 3. So inside the root we left only 5. So in total we found out that MP equals to 3 times square root of 5 units in its name. This is side MP, the hypotenuse MP is equals to 3 times square root of 5 units in its name. In the next step we focus on those two right angles. Actually, first of all we know that in square ABCP all the angles are equal to 90 degrees, and therefore this is a right angle. And in the big square TSQP all the angles are also right angles, and therefore this is a right angle. So in the next step we focus on those two right angles. This is the small right angle TBM, and this is the big right angle AMP. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, one solver, and therefore they are equal to each other. So we should know that all the three angles of the small right triangle TMB are correspondingly equal to all the three angles of this big right angle AMP, and therefore those two right angles are similar to each other according to angle similarity rule. And again, if we know that the big right angle AMP is similar, this is the sign of similar, to the small right angle TMB according to angle similarity rule. And from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side AP of the big right angle AMP over side TB of the small right angle TMB equals to side MP of the big right angle AMP over side MB of the small right angle TMB, and it is also equals to side AM of the big right angle AMP over side TM of the small right angle TMB. And again, from the fact that those two right angles are similar to each other, we derive that AP over TB equals to MP over MB equals to AM over TM. AP is 6, TB is the missing size of relativities. MP, what is the length of side MP? We already found out that MP equals to 3 over square root of 5 over MB. MB equals to AB, that is 6, because one side of square ABCP equals to 6, minus AM, that is 3. So MB equals to AB, that is 6, minus AM, that is 3. So MB total equals to 6 minus 3, that is 3. So MB equals to 3. And it is equals to AM. AM is 3 over TM. TM is the missing size of relativity. So in total we should find out that 6 over TB equals to 3 times square root of 5 over 3, and it is equals to 3 over TM. We have 3 in the numerator and 3 in the denominator, so 3 will get cancelled, and we left only square root of 5. Those two sides are equal to each other. Yeah, those two sides are equal to each other. That is to say, 6 over TB equals to the square root of 5. Again, 6 over TB equals to the square root of 5. Here we multiply this equation by TB, and then we divide it by square root of 5 simultaneously. And we found out that TB equals to 6 over square root of 5 units in its length. This is the missing side TB. This equals to 6 over square root of 5 units in its length. those two sides are also equal to each other. That is to say, square root of 5 equals to 3 over tm. Square root of 5 equals to 3 over tm. Here we multiply this equation by tm, and then we divide it simultaneously by square root of 5, and actually found out the tm equals to 3 over square root of 5 units in its length. This is the missing tm that is equals to 3 over square root of 5 units in its length. What is the length of side TP of square, the big square TSQP? TP equals to TM plus MP. And TP equals to TM plus MP. And TP equals to TM plus MP. TM equals to 3 over square root of 5. No, TM equals to 3 over square root of 5 plus MP, that is 3 times square root of 5. And again, Tm equals to 3 over square root of 5 and MP equals to 3 times square root of 5. So in total, Tp equals to 3 over square root of 5 plus 3 times square root of 5. Here we multiplied 3 times square root of 5 by square root of 5, and then we divided by square root of 5 in order to come in front of this number. So here we have 3 over square root of 5, and we multiplied 3 times square root of 5 by square root of 5, so square root of 5 times square root of 5 is 5, and 5 times 3 is 15, divided by square root of 5. 3 plus 15 is 18 over square root of 5. So in total we shall note that Tp equals to 18 over square root of 5 units in its length. This is side Tp, this is equals to 18 over square root of 5 units in its length. Our test is to find out the area of this range shape. The area of this range shape must be equal to the area of the big square TSQP minus the area of this quadrilateral MBCP, that is 27, minus the area of this small right triangle TMB. And again, the area of the range shape in total equals to the area of the big square TSQP minus the area of quadrilateral MBCP, that is 27, square units in its size according to what is given in the question, minus the area of the right triangle TMB. So the area of square TSQP equals to TP squared, that is one side squared, TP squared, minus the area of the quadrilateral MPCP. The area of this quadrilateral MPCP is 27 square units inside according to what is given in the question, minus the area of the small right triangle TMB. The area of this small right triangle TMB equals to the base TB times the ITM over 2. And again, the area of the small right triangle TMB equals to the base TB times the ITM over 2. So in total, the area equals to the area of the big square, that is TP square. TP is 18 over square root of 5, therefore TP square is 18 over square root of 5 squared, minus the area of the quadrilateral MPCP, that is 27 square units inside according to what is given in the question, minus the area of the small triangle, TMB, is equals to TB. TB is 6 over square root of 5 times TM. TM is 3 over square root of 5 divided by 2. So here we have 18 over square root of 5 squared is 18 squared, that is 324 over square root of 5 squared, that is 5, minus 27. And we have here in the numerator of 6 times 3, that is 18. In the numerator we have square root of 5 times square root of 5 is 5, and 5 times 10, 5 times 2 is 10. So in total, the value of this expression is equal to minus 18 over 10. 324 over 5 is 64.8, minus 27, and 18 minus 18 over 2 is minus 1.8. And we have 64.8 minus 1.8 is 63. So total this expression equals to 63 minus 27. So total we should find out that the area of the green shape equals to 63 minus 27, that is 36. So if you find out that the area of this green shape, that is the area that we are looking for this question, it is equal to 36 square units in its size. So we finish with the first question. The next step I presented to the second question and we solve the second question of this lecture. The second question, our test is to find out they are this ring shape. So in the drawing we have square ABCD. We know that one side of square ABCD equals to 10 units in its length. In addition, inside this square we have this quarter circle. The center of the quarter circle is 8.8, and we have this semicircle. The center of this semicircle is 8.0. Again, our test is to find out the area of this ring shape. So first of all, we define the center of this semicircle. This point is 0.0. We know that the diameter of BC is 10, therefore the radius must be equal to 5. The radius of B is 5, the radius of C is also 5. And we have here the quarter circle. We know that the center of the quarter circle is 8.8. Point D is the point of the quarter circle itself, therefore AD is the radius of the quarter circle, that is 10, because one side of the square is 10. So in the next step, we join points O and M together by a straight line. Point O is the center of the semicircle, point M is the point of the circle on the semicircle itself, therefore OM is the radius of the semicircle, that is equals to 5. In the next step, we join points A and M together by a straight line. What is the definition of AM? AM is the tangent to the semicircle at point M. So here we can implement rule 1, because we have the radius OM that is equal to 5. The radius OM is drawn to point M, that is the point of tendency, and then AM will be semicircle. And remember, your radius that is drawn to the point of tendency, then tangent AM will be perpendicular to the radius MO. If AM is perpendicular to MO, it means that this angle equals to 90 degrees. So, in the next step, point A is the center of the quarter circle. Point M is the point of the circle, the quarter circle itself, yeah? And therefore AM is the radius of the quarter circle, that is equal to 10. You know that AB equals to 10 according to what is given the equation. It is one side of square ABCD. So in the next step, we join points A and O together by a straight line. This angle is a right angle because it is 1 out of 4 angles of square ABCD. We know that all the angles inside the square are right angles. This angle equals to 90 degrees according to rule 1. Okay? In the next step, we prove that those two right angles can point to each other according to side rule. We have the right angle AOB that is congruent to the right angle AOM according to side rule. So why those two right angles can point to each other? First of all, side OB equals to side OM, they're both equal to 5 and therefore they're equal to each other. In addition, side AB of the triangle ABO equals to side AM of the triangle AOM. They are both the area of the quarter circle, that is equal to 10, and therefore they are equal to each other. And finally, side AO equals to itself. It is a common side that belongs to both triangles, so I can write down that AO equals to itself is a common side that belongs to both triangles. So in total, we can find out that all the three sides of the right triangle ABO corresponding equal to all the three sides of the right triangle AOM, and therefore those two right triangles can point to each other according to side rule. And again, we can find out that the right triangle ABO can point, this is the sign of can point, to the right triangle AOM according to side rule. And from the fact that those two right triangles can point to each other, we know that those two angles must be equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. That is to say, those two triangles can point to each other, and therefore those two corresponding angles must be equal to each other and their sizes. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. And from the fact that those two right angles can point to each other, we derive that those two angles must be also equal to each other according to the same rule that corresponding angles in congruent triangles are equal to each other. So if we define this angle as beta, then this angle must be also equal to beta because they are equal to each other according to the rule that I mentioned. So we have in the right triangle AOB, the sum of the angles must be equal to 180 degrees. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right triangle AOB? We have this angle alpha, this angle beta, this angle is right angle. So alpha plus beta plus 90 degrees must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the right triangle AOB, alpha plus beta equals 90 degrees equals to 180 degrees. Here we subtracted 90 degrees from this equation. If we found out that alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. Here we subtracted alpha from this equation and found out that angle beta equals to 90 degrees minus alpha. In the next step, we implemented the Pythagoras theorem on this right triangle ABO in order to find out the length of the hypotenuse AO. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle AOB, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. And again, in the right triangle AOB, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. AO is the missing side, so it is, and it is equals to AB squared. AB is 10, therefore AB squared is 10 squared, that is 100, plus BO squared. BO is 5, therefore BO squared is 5 squared, that is 25. So in total, we will know that AO squared equals to AB squared, that is 100, plus OB squared, that is 25. 100 plus 25 is 125. So in total, we will know that AO squared equals to 125. We substituted 125 by 25 times 5, and so in total, we found out that AO squared equals to 25 times 5. Here we took out of this equation, and we found out that AO equals to the square root of 25, that is 5, so inside the root we left only with 5. So in total, we actually found out that AO equals to 5 times square root of 5 units in its length. Therefore, AO equals to 5 times square root of 5 units in its length. In the next step, we continue to focus on the right triangle AOB. In the right triangle AOB, sinus alpha equals to BO over AO. Sinus alpha equals to BO over AO. So sinus alpha equals to BO, that is 5, over AO, that is 5 over square root of 5. Repeat again, in the right triangle ABO, sinus alpha equals to BO over AO. BO is 5, AO is 5 over square root of 5. So in total, sinus alpha equals to 5 over 5 times square root of 5. We have 5 in the numerator, 5 in the denominator, so 5 will get cancelled, and finally found out that sinus alpha equals to 1 over square root of 5. So sinus alpha equals to 1 over square root of 5. Our task is to find out the value of alpha itself. In order to find out the value of angle alpha itself, we must operate the opposite function of sine, that is arc sine, on the result. This will give us the value of alpha itself. So the opposite function of sine is arc sine, so arc sine of 1 over square root of 5 is equal to alpha. And arc sine of 1 over square root of 5 is 26.565 degrees. So in total, we should know that angle alpha equals to 26.565 degrees in its size. And therefore 2 alpha must be equal to 2 times 26.565, that is 53.13 degrees. And we only found out that beta equals to 90 degrees minus alpha. Here. Beta equals to 90 degrees minus alpha. Beta equals to 90 degrees minus alpha. So beta equals to 90 degrees minus alpha, and alpha equals to 26.565. So in total, beta equals to 90 degrees minus 26.565 degrees, and 90 degrees minus 26.565 degrees is 63.435. So beta equals to 63.345 degrees, and therefore 2 beta must equal to 2 times 63.345, that is 126.87 degrees. So in total, we should find out that 2 alpha equals to 53.13 degrees, and 2 beta equals to 126.87 degrees. This is the big angle 2 alpha is equals to 53.13 degrees, and this is the big angle 2 beta is equals to 126.87 degrees in its size. Our task is to find out the area of this grand shape. So the next step, we join points M and B together by a straight line. By joining points M and B together by a straight line, we divided the grand shape into 2 segments. We have the upper segment MUB, and we have the lower segment MLB. So we will calculate the area of this each segment separately, and then relate the two areas together. This will be the area of this ring shape. So first of all, I copied sector ABM, and in Olympiad we analyze this sector. This is sector ABM, the point of the original domain. First of all, what is a sector? A sector is a portion of a circle enclosed by two radii and the arc between them. And again, the ring shape AOB is a sector. A sector is a portion of a circle, as you can see, enclosed by two radii. Those are the two radii of the circle, and the arc AB between them. The angle between the two radii defined as the length of the sector. The angle between the two legs of the sector is theta. So a sector is a portion of a circle enclosed by two radii and the arc AB between them. And the area of this sector, sector AOB, equals to pi r squared, that is the circle that contains the sector, times the angle between the legs of the circle, that is theta, over 360 degrees. Repeat again, the area of sector AOB equals to pi r squared, that is the circle that contains the sector, times the angle between the legs of the circle, that is theta, over 360 degrees. So we use the new formula in order to find out the area of this sector, sector ABM. According to the, we know that AM equals to AB equals to 10. AM equals to AB equals to 10. The above the radii of the quarter circle is equal to 10, and therefore they are equal to each other. The angle between the legs of the circle is 2 alpha. That is 53.53 degrees in size, according to what we have already found out. This is the angle between the legs of the circle. So according to the formula that I presented to you in the beginning of the lecture, and the beginning a couple of minutes ago, the area of this sector A and B must be equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the circle, that is 53.13 over 360 degrees. Okay, again, the area of the sector A and B equals to pi r squared times 53.13 over 360 degrees. R is 10, therefore r squared is 10 squared, it is 100. So pi r squared is 100 pi times 53.13 over 360 degrees. In total, the value of this expression, 100 pi times 53.13 over 360 degrees, is 46.3646 square inches in size. So in total, we should find out that the area of this sector A and B equals to 46.3646 square inches in size. Our test is to find out the area of the lower segment MLB. So what is the area of this lower segment MLB? From the drawing, it is very easy to see that the area of this lower segment MLB or BLM equals to the area of the big sector A and B minus the area of triangle A and B. Again, the area of segment BLM equals to the area of sector A and B minus the area of triangle A and B. It is very easy to see that if you subtract from the area of the sector A and B the area of this triangle A and B, we get the area of segment BLM. Okay, again, the area of segment BLM equals to the area of sector A and B minus the area of triangle A and B. We already found out that the area of sector A and B equals to 46.3646 units in size minus the area of this triangle A and B. If we present it to you in a formula, that we have asked to find out the area of any triangle. This is triangle A and BC. This is triangle ABC that could be in a triangle. Side AB equals to A units in itself, side AC equals to B units in itself, and the angle between side AB and side AC is theta. The area of this triangle, triangle ABC that could be in a triangle, equals to A times B, that is the multiplication of the two sides by each other, times the angle times sinus the angle between the two sides, that is theta, over 2. So in total, the area of this triangle ABC that could be in a triangle equals to A times B times sinus theta over 2. We use the new formula in order to find out the area of this triangle ABM. So according to the formula that I presented to you here, now the area of this triangle ABM will be equal to AB times AM times sinus angle 53.13 over 2. And now this angle ABM equals to AB times AM times the angle between the two sides times the angle between the two sides, that is 53.13 over 2. AB is 10, AM is also 10, and sinus 53.13 is 0.8. So in total, there this angle ABM equals to 10 times 10, that is 100, 100 over 2 is 50, and 50 times 0.8 is 40 square meters in size. So in total, we found out that the area of this triangle ABM equals to 40 square meters in size. And our test is to find out the area of segment BMM. The area of segment BMM equals to the area of sector A and B, that is 46.3646, minus the area of this triangle ABM, that is 40. 46.3646 minus 40 is 6.3646 square meters in size. So in total, we found out that the area of this lower segment BLM equals to 6.3646 square meters in size. So in the next step, we'll find out the area of this upper segment BUM. We already found out that the area of this lower segment BLM equals to 6.3646 square meters in size, and in the next step we'll find out the area of this upper segment BUM. In order to find out the area of this upper segment BUM, I copied sector OMB, and in operation analyze the sector OMB. This is sector BOM or OMB, the copied from the original drawing. The rounded sign above BOM is a sign of a sector. This is sector BOM. We know that the two legs of the sector are the two at the end of the semicircle, that is 5, and the angle between the two legs is 2 beta, that is 126.87 square units. And according to the formula that I presented to you a couple of minutes ago, the area of the sector BOM must be equal to pi r squared, that is the area of the circle that contains the sector. Okay. Of the circle that contains the sector, and r is 5, times the angle between the legs of the sector, that is 126.87 over 360 degrees. R is 5, therefore r squared is 5 squared, that is 25, so pi r squared in total is 25 pi, times 126.87 over 360 degrees. In total, the value of this expression, 25 pi times 126.87 degrees over 360 degrees. In total, the value of this expression is 87.678 square meters in size. So, in total, we should find out that the area of this sector BOM equals to 27.678 square meters in size. Our test is to find out the area of this upper segment BUM. So, what is the area of this upper segment BUM? From the drawing, it is very easy to see that the area of this upper segment BOM equals to the area of sector BOM minus the area of triangle BOM. Again, the area of sector BOM minus the area of triangle BOM equals to the area of segment, the upper segment BOM. We already found out that the area of sector BOM equals to 27.678 square meters in size minus the area of this triangle BOM. You know that BO equals to 5, OM also equals to 5, and the angle between the two sides is 2 beta, that is 126.87 degrees. So according to the formula that I presented to you a couple of minutes ago, the area of this triangle BOM must be equal to BO times OM times sinus angle 126.87 degrees over 2. BO is 5, times OM is also 5, so 5 times 5 is 25. Sinus 126.87 is 0.8. So in total, the area of this triangle BOM equals to 5 times 5, that is 25. 25 over 2 is 12.5, and 12.5 times 0.8 is 10. So in total, we should find out that the area of this triangle BOM equals to 10 square meters in size. In total, the area of the upper segment BOM equals to the area of sector BOM, that is 27.678, minus the of triangle BOM, that is 10. The 27.678 minus 10 is 17.678 degrees in its size. So in total, we should find out that the area of the upper sector BUM equals to 17.678 degrees in its size. So in total, we should find out that the area of the upper segment BUM equals to 17.678 degrees in size, and we already found out that the area of the lower segment BLM equals to 6.3646 kilometers in size. And the area of this green shape, of course, equals to the area of the upper segment BUM, that is 17.678, plus the area of the lower segment BLM, that is 6.3646 kilometers in size. 17.678 plus 6.3646 in total is equal to 24.042 square meters in size. So the answer to the question is that the area that we are looking for in this question, that is the area of this green shape equals to 24.04.2 square meters in size. Okay, thank you very much.